Green's theorem. First of our three big theorems. Let D be an open, simply connected region with a boundary curve, partial D, that is a piecewise smooth, simple, closed curve, oriented counterclockwise. Let F be a vector field with component functions that have continuous partial derivatives on D. Then circulation over the boundary of D of F is the double integral over D. Partial Q partial X minus partial P partial Y. Where P is your first component, Q is your second component of the vector field. What Green's theorem allows us to do is calculate the circulation as a double integral. So we're going to go ahead and verify Green's theorem. Region, where C is the boundary of the region bounded by x and x squared. This larger. Oh god, it's way too big. The beautiful thing with this is I can calculate this. So when dealing with Green's theorem, if you want to plot the region and the curve, you have to remember that orientation now matters. That's also true for line integrals. Orientation matters. So if you want to plot arrows, you have to go under plot style and arrowheads. I have to do one for each curve, right? Because I have two curves here. The first number represents the size of the arrow. Second number represents a position. And I think both are between 0 and 1. I know for a fact the position is between 0 and 1. 0 being the starting point, 1 being the end point. To switch the direction of the arrow, you just put a minus in front of the size. Right, so normally, y equals x has a direction along this way, right? But that's not counterclockwise. So I have to switch the direction, so I just put a minus in front. This is our region, along with its boundary. Let's quickly save this. What medium is this? 37. Our vector field. There. There's the vector field. With this problem, I'm going to write out what P and Q are. My first component is xy plus y squared. Second component, q, x squared. Remember, we're verifying Green's theorem. That means we have to calculate both sides. We have to calculate the circulation, and then we have to calculate the double integral and show that they are the same. Keep in mind, verifying is not a proof. Right? We're not proving Green's theorem. We're just verifying that Green's theorem holds for this specific vector field and this specific region. In fact, the full proof of Green's theorem is really complicated. I think it's a graduate level proof. Let's start with the left-hand side first. So let's start with the circulation. We need to parameterize our path. What do you notice? If you're walking along that path, you essentially have two separate paths that you're walking, right? So our curve, which is the boundary of our region, union of two curves. And since it's circulation, it doesn't matter where we start, right? Where we start to walk doesn't matter. So let's just start here at the origin. We say that is our starting point. C1 would be that curve, right? And then C2 is that return. So C1 we're going to say is x squared, C2 is x. Parameterization for C1. It's a really obvious parameterization. Isn't the path y in the form y equals a function of x? So why not use that as your parameter? X is your parameter. What would your y component be?
One.
Again, what is it? In terms of the parameter. You're overthinking. What does y equal?
X.
First half. That bottom one. So that's your y component. That's your parameter. X goes from 0 to 1, right? R2, second path, there's actually two convenient parameters to use. Parameterizations, rather. We did one before. I have to go back to that square. Last week we did line integrals and surface integrals. When we did that square, that's one parameterization you can use. I'm actually going to go this way. And there's a reason for that. R1 prime, 1, 2x, right? R2 prime, 1, 1. Yes? So our circulation would be the integral on C1 minus the integral on C2. Why is it minus and not plus? Because remember the one we did last week, we had the union of curves. We added both the integrals together. Why is it minus here?
Is it because of the path?
What about the path?
It goes like different ways.
The way that I parameterized the second path was in the opposite direction of the actual direction. So I'm going to subtract instead of add. That is another trick you can use when you're doing parameterizations. Right? In this case, it's more convenient for me to parameterize it in the opposite direction. So I'll just multiply the result by -1. And then go from 0 to 1. We need to evaluate our vector field along the parameterization. X is x, y is x squared. I'm going to keep it in this form. X times x squared. Then it was what? X squared squared times dx which stays as dx, 1 times dx, plus x stays the same, x squared times dy, but dy is 2x dx. That would be the replacement. Minus the integral from 0 to 1. X times x plus x squared. R2 prime is 1 comma 1. Dx is dx. Plus x squared times 1 dx. Be like that, wouldn't it? We can now write that as a single integral, can't we? And with it being 0 to 1, that makes this really nice. Antiderivative of x to the 4th is x to the 5th over 5, right? From 0 to 1, excuse me, isn't that just 1/5? Three x cubed, 3/4 x to the 4th, but that goes from 0 to 1. And then 3x squared is just x cubed. Four plus 15 is 19. Minus 20 is -1. There's the circulation. -120.
Can you go over how you got the parameters for x and x squared for the first one?
What's the curve?
X squared.
More specifically, write it as an equation.
Y equals x squared.
Y equals a function of x, right? Let x be a parameter.
How do you get the x for the, oh, okay. Gotcha.
Right, and then your second would just be the function itself.
Okay.
Right, much like, remember when we were doing the surfaces, if you can write the surface as z equals a function of x and y, then x, y are parameters, and then z would be whatever the function itself is. It's the same idea.
Okay.
Is that the only parameterization? No, but it is the easiest.
I guess if you want to put it in functions of x, you could do it the opposite way then.
The functions of y?
Or functions of,
Yes.
Yeah.
You could let y be your parameter, and then x would be whatever the function of y was. Now for the right-hand side of Green's theorem, the double integral. You need partial q, partial x. So what's partial q, partial x? We also need partial p, partial y. What's partial p, partial y? We also need a description for the region. So now it's going to require you to go back to when we studied double integrals. See what I said? This is tying everything that we've done in calculus all together. Remember you had two options, vertically simple or horizontally simple. Vertically simple probably be the best. X is going to go from 0 to 1. Then what is y going to go?
x to,
What is it? X squared to x. Integral 0 to 1, integral x squared to x. X minus 2y. dy dx. That's what we're evaluating. Integrate first with respect to y. The x minus x squared, all times x. X squared minus x cubed, then it would be minus the quantity x squared minus x to the fourth.
Yeah.
No, it should be x squared.
Are you multiplying x squared by x though?
That was the first one. Minus y squared.
Yeah, x times x squared minus x squared squared.
X times x squared, right?
Yeah.
That goes from x squared to x. That's x minus x squared, isn't it?
Oh yeah, yeah.
And then distribute your x though.
Okay.
This is just y squared. X squared minus x squared squared. That's where you get the x squared minus x to the fourth, right? X to the fourth minus x cubed from 0 to 1. It's just a fifth minus a quarter, isn't it? 4 minus 5. Negative 1. Is that what we got for the circulation? It is, right? That verifies Green's theorem. That means you can get a problem like this, you can either do the line integral, or you can do a double integral by setting up Green's theorem. And then you can choose whichever one, you can just do whatever one's easier. 9 times out of 10, using Green's theorem is going to be easier. And doing the double integral is generally going to be easier. Oh, that's something's wrong there. That looks better. Let me evaluate this line drill. C is the path. X to the fourth minus 6xy cubed equals 4y squared from 0, 0 to 2, 1. Now it's better. So what I did here, same thing for the path, except I use contour plot instead. Notice I defined it as path, and then I defined an initial point and a terminal point. Graphics is a very nice feature. Used to do a lot of surprise graphics. The point size command obviously is going to say how large the point's going to appear, and then you have the point command. And then I just showed all three together. Here's our path. What do you notice about that? Didn't even need the plot to see it, but
It's finite.
what do you mean finite?
Goes from 0 to 2 on the x.
Sure. All paths are finite. But
There's-
that's not true, but all paths that we're going to deal with are finite. It's a very important feature. What was that path?
It was a circular.
What's the term for that?
Yeah.
It does begin with C.
And yeah, I forgot.
It's closed.
Close, there you go.
Is that closed?
No.
You can't use green stamp. Green stamp is only for closed curves. This one is not closed. I mean, you cannot use Green's theorem. You need to parameterize that. Oh dear. That is going to not be fun. Oh, but would we be able to use the fundamental theorem of line integrals? Because if this is path independent, this just became a lot easier. When would it be path independent? What's the condition for path independence? Go back to last week. If I'm not mistaken, last Tuesday. when is a path, or when is a line angle path independent? Well, that is path independence, but when can you do that? It's not true for every vector field. It's only true for a certain kind. Your vector field has to be conservative. If our vector field is conservative, we can do path independence. Check. No, I'm sorry, that's partial x. You want partial x of your y component. Negative 6xy squared, right? Partial y of the x components. Negative 6xy squared. Are they the same? This is path independent. These are called your cross partials. Right, so the test that was given was for the three-dimensional vector field, right? It was the curl. But it's the same thing as saying that your cross partials are the same. When you're dealing with 2 dimensions, you don't really have to worry about the curl. Just partial x of the y component and partial y of the x component. If they're equal, it's conservative. What you could do is try and find a potential function, but I actually find that to be pretty difficult in this case, or at least more difficult than what I'm going to do. I'm just going to integrate along that path instead. That's what path independence means. That's just a straight line. That is the line that connects 0, 0 to 2, 1. So what's the equation of that line?
What half x?
Y equals x over 2. I'll just keep it on here. Parameterization. I'm actually going to go 2y comma y to avoid the fraction. Y goes from 0 to 1. Right, x is 2y, so what's 2 to the 4th?
16.
Times 10?
What's 16?
And it would be what? 4y to the 4th minus 4y to the 4th. Again, x becomes 2y, and y stays the same. But what is dx? Two dy, right? Two squared, 4 times 3 is 12. And dy stays as dy, it's 1 dy. $160 minus 4, 156. 156 times 2. 312. 312 minus 12, oh, look at that, that's nice, 300. What's the antiderivative of y to the 4th?
Y to the 5th, or 5?
Divided that from 0 to 1.
1/5.
300 times a fifth. There's your interval. Again, I found that to be easier than trying to find the potential function. You can still find the potential function if you want to. And then be v, right, it'd be v of 2 comma 1 minus v of 0, 0, which will still be 60.
So if it's a line independent, you can
Path independent.
path independent.
You can either find the potential function and then do v of the final point minus v of the initial point, or path independence means any path.
So you could do any function from those 2 points,
No, not any function.
or any path along.
You can just do a different path.
Okay.
The simplest path being the straight line that connects them. I say straight line, that's redundant, right? All lines are straight. Just do a line, the straight path that connects the 2 points.
Okay.
Generally speaking, that's probably going to be simpler than finding the potential function. Simpler, I mean quicker. This problem might be important. We're going to show that the area bounded by a simple closed curve is given by that. If C is a simple closed curve that encloses the region D, that is, C serves as the boundary for D. Bada-Bing's theorem. That line integral is going to be the double integral partial x of the y component which is x, minus partial y of the x component, which is negative y, dA. What's partial x of x then? Which is pretty easy. What's partial y of negative y?
Negative.
One plus one is 2 times a half is 1. So that's just double integral dA, right, over the region. What's that double integral represent? Comes when you integrate over a region, just dA.
The area.
It's just the area of the region. Oh, it is not what we wanted? The proof is complete. So what this will allow you to do is to essentially use Green's theorem in reverse. Right, remember we were trying, actually I think we did volume, didn't we? Volume of an ellipsoid, let's just say area of an ellipse. Well, an ellipse, the parameterization of an ellipse isn't really that nice, which makes double integrating pretty hideous. I'm not mistaken. That's actually what the next question is. Find the area of the ellipse. But if you just look at the boundary of the ellipse, right, that's going to have a certain parameterization, specifically this, it's going to be a lot easier using this formula to find the area. So I can't remember if there's a question like that on the exam. There might be, or it asks you to use, or maybe the quiz, where it asks you to use Green's theorem to find area. This is what they want. So again, this is one you might want to mark off. It's really important. Any questions so far on Green's theorem? So I think that's where I'll stop. I did mention it on Friday. There was a quiz that went up. I extended the due date because I did forget to mention it. So quiz 4 is up and it is now due Thursday. If you already did it, if you did see it, you did it. Original due date was Tuesday, you're fine.
Oh, I thought it was always Thursday.
But I did extend it to be Thursday, so if you haven't taken it yet, take it. I'm fairly certain I did extend it, so if you don't see it, please let me know. So I can go in and fix that. I think I did it already. And then the Green's theorem homework is up, but it won't be due until May 1st. We'll continue with Green's theorem on Thursday. See you then. Oops. Yes, Green's theorem.